With today's technology, whether humans can colonize centaurs with alpha coefficients has become a fascinating topic. Think about it. If someone tells you, with our current technology, we can reach Centauri's alpha coefficient in 50 years. Does this sound very shocking? In this challenging era, even traveling to Mars, it's kind of out of reach. But actually, after some exploration and understanding, you'll find that this idea is not groundless. In 1958, the Orion project was born. Directed by nuclear physicists Ted Taylor and Freeman Dyson, their ambitious goal is to build a nuclear-powered rocket. This rocket can send a spacecraft to Mars in a very short time. Not even more than one human, to a place as far away as Alpha Centauri coefficient. However, for space explorers, the Orion plan has one drawback that cannot be ignored. That's his dependence on turtle fuel. This not only causes serious environmental pollution, it's also energy inefficient. A better solution is to use nuclear fusion technology. Although fission technology has been used, and the technology to build Orion has been around for more than 40 years. However, humans have not yet achieved effective control of fusion energy to the Alpha Centauri coefficient. We need a completely different propulsion technology. It is now relatively easy to reach the Moon and other planets using low-thrust orbits or top propulsion technology. These two approaches are undoubtedly the most effective ways to explore the inner solar system. But as the target gets farther and farther from Earth, the challenges we face are also growing. Even Mars. It is also an inaccessible goal. Current Mars colonization plans are expected to take months or even years. To ensure the safe landing of the spacecraft, usually this process takes about 9 months. Think about it. How difficult it would be to execute such a task. Astronauts need to learn how to live continuously in the confined space of a machine for 9 months. This is undoubtedly a great challenge in the core of the body. Despite this, the scientific community is working hard to explore. We have reason to believe, and that dream will come true, and it may be sooner than you think. It is worth mentioning that there is a potential solution. Maybe it will get us in a shorter time, arriving at Mars in about 2 months. As unbelievable as this may sound, but it wasn't actually parachuting. In the late 1950s and early 1960s, the US government-backed LIHU project shows mutual. The possibility of sending exploration reactors to Mars or even Saturn. The project also plans to establish a lunar base staffed by about 150 highly skilled scientists. 7-year study period. The Orion project has come up with many exciting ideas and concepts, and these are still valuable today. The design idea of Orion's plan is very unique. Plans to detonate an atomic bomb about 61 meters behind the spacecraft. To propel the spacecraft to amazing speeds. This concept of atomic propulsion was just a science fiction idea in the 1930s. But by 1944, people began to pile up within the framework of spaceflight for serious study. In that period, scientists are dedicated to developing various propulsion engines. The basic principle is to pump working fluid into a nuclear reactor for heating. And then the nozzle expands to create thrust. Although this may seem simple, but there are challenges. However, if you can successfully build an atom-propelled spacecraft, it will bring unprecedented glory to humanity and make a huge impact in the first country to show a working prototype. Such an engine would harness the power of an atomic bomb. Its power is estimated to be around 74.6 million kilowatts. By spraying bombs and subsequent solid propulsion disks backward, the explosion will vaporize the propulsion chessboard. The resulting ion barrier hits the propulsion plate to propel the spacecraft forward. The advantage of this system is that he doesn't try to limit the force of the explosion. This means higher yield bombs can be used, so they get more thrust. This system is not limited by temperature. It's not limited by power. The calculation results of the thrust show that the force acting on the propulsion plate is tremendous, enough to cause unbearable acceleration for a manned vehicle. So the designers put shock absorbers in between the propulsion and the non-economy to mitigate this effect. The durability of the advanced version becomes a key consideration, but it has been experimentally verified. The durability of aluminum or steel is considered sufficient to meet the requirements, can be used as a material for pushing gold plates. Ted Taylor and Freeman Dyson were responsible for formulating plans for manned travel to the solar system. Orion's design requires 2,000 pulse units to provide enough thrust to escape Earth's attractive forces, and is expected to reach 5% of the speed of light. This speed will enable humans to reach the closest star system to us. The spacecraft will be built in a warship-like manner. No need for weight reduction measures common in other space flag designs. How Orion landed at its destination remains unclear. It may be carried out with the help of specially designed chemical-powered spacecraft. The total duration of the character exploration program is 12 years. It costs $100 million a few years, but that may not include all the development costs. Orion's plans are likely to rely on existing military and civilian space program resources. Even if the cost estimates vary, the revised total cost remains $24 billion. Similar to the cost of executing the Apollo program. To thoroughly evaluate the feasibility of an Orion program that relies on an explosive nuclear reaction, the plan involves a series of tests. These tests will detonate small box devices in Earth's atmosphere to obtain key data on the efficiency and capabilities of the proposed propulsion system. However, international agreements during the Cold War brought the era of atmospheric nuclear testing to an end, mainly due to concerns that radioactive fallout poses no potential harm to the environment and human health. Such tests are banned by the international community. The crucial role played by the Comprehensive Nuclear Test Ban Treaty in shaping this global consensus. The world's major countries are aware of the potential danger of radioactive debris spreading during a strike. It is important to note that what was forbidden was atmospheric testing, rather than underground testing. The latter continued for some time after the ban on atmospheric nuclear testing, allowing countries to verify nuclear weapons without generating air pollution, improve its nuclear arsenal. This geopolitical context had a major impact on the Orion program. The ban on atmospheric nuclear testing has become a major obstacle to its development. This eventually led to the cancellation of the project in the 1960s. Although the Lihuzo project was terminated due to geopolitical and environmental concerns, but its potential for space exploration is still widely recognized. If nuclear testing is not banned, and environmental and safety issues are properly addressed, he may be able to provide a viable technological avenue for future star travel. However, the practical application of this concept requires comprehensive consideration of environmental impact, safety measures, international cooperation, technological progress, and ethical issues, among other factors. Despite the controversy, but this approach may represent an existing technological approach. To be able to realize the dream of traveling to new star systems of the magnitude of Centauri as alpha coefficients. The alpha coefficient Centauri system is a complex system of 3 stars, including the Centaur alpha coefficient, Centauri alpha coefficient, and Bilixing. Together, they form the closest star system to us, only 4.2 light-years from Earth. This system is of particular interest to scientists because some exoplanets orbiting Bilin may have potentially habitable conditions. The frontier is located within its zone. It is possible that liquid water exists. The habitability of the frontier has become the focus of extensive discussion and research in the scientific community. To accurately evaluate this line, whether love ends in the drama of life, we must consider, including rampant activity and tides, multiple traces locked there. Alpha Centauri coefficient is similar to Jasper, our sun. They're orbiting each other in a binary star system, and it's relatively close. Alpha Centauri coefficient star is a GRV-type star. Its quality, radius, and brightness slightly higher than the Sun. The Centauri alpha coefficient star coin is a slightly lower temperature, smaller K1V stars. The temperature distribution of these 2 stars is between 5,260 and 5,190 Kelvin, compared to the temperature of the Sun, which is around 5,872 Kelvin. Both stars are important subjects for the study of potentially habitable exoplanets. Despite this, so far no confirmed teardrop planets have been found within their base belt. Exploring the Alpha Centauri coefficient star system is not just about unlocking the secrets of this galaxy, but it also allows us to think deeply. If we can use Orion for the propulsion system envisioned in the plan, will the dream of getting there ever come true? Now imagine this. We're going to send a space probe to Alpha Coefficient Centauri, about 437 light-years away. The goal is to get there by 2,120 years. From now to the target year, we have a total of 96 years. Converted to hours, this is equivalent to approximately 60 hours. To achieve this ambitious goal, our spacecraft needs to maintain an average speed, approximately 30,441,400.3 kilometers per hour. This is equivalent to about 4.5% of the light family. According to Dyson's extensive analysis during the early stages of the Orion program, it is theoretically possible to accelerate a spacecraft to about 5% of the speed of light. Considering that our target speed is 4% of the speed of light, and Dyson claims to be able to reach 5%, we can infer it is theoretically possible for humans to reach a Centaur alpha coefficient star within a human lifetime. Starshot is another ambitious project. He is backed by Russian billionaire Ranelna and launched a few years ago, rekindled humanity's dream of exploring nearby star systems. The plan is to launch nano spacecraft, flying to our nearest neighbors at an astounding 20% of the speed of light. Alpha Centauri coefficient star system. This means that humans could arrive there in just 20 years. Inspired by the concept of Starshot, scientists at the Max Planck Institute in Germany have developed a groundbreaking method so that the spacecraft can slow down once it reaches its destination. This is achieved by exploiting stellar pressure. If the spacecraft were to take images or collect scientific data upon arrival, so how to effectively slow down becomes a joint problem. NASA recently introduced a revolutionary program. The Breakthrough Advancement Architecture, known as the Star New Area mission, marked the dawn of a new era of space exploration. The goal of this research is to use laser technology to transmit electrical energy within the solar system. Inspira's groundbreaking launch plan. The project also envisions an extremely efficient solar photovoltaic array, an astonishing 60 to 70% efficiency. And it's powered by lithium-ion propulsion. The combination of these advanced technologies reflects humanity's growing interest in interstellar travel. Through the Breakthrough Interstellar program and NASA's Advanced Propulsion Technology program, we have taken an important step towards realizing our dream of exploring other star systems in the universe. And pattern change is another effective way to achieve perseverance. His goal is to simulate the workings of the sun, copy the conditions of the sun by forcing atoms and fusing under extreme temperatures and pressures. To keep the fusion reaction under control, the management of high-temperature plasma proposes a series of innovative methods. Each approach faces challenges in its stability and containment. Achieve competitive energy output and ensure that the reaction releases more energy than is required for its operation. Is the key to nuclear fusion as an energy source. In addition, materials science also faces challenges, because the extreme environment inside fusion reactors requires the use of long-term resistance to high temperatures and neutrons. Impetuous and non-degrading materials. This further complicates the engineering and design of fusion reactors. At the end of this journey of discovery, we reviewed the infinite possibilities that technology has revealed to us. And think about possibilities like how to get us close to the coveted Alpha Centauri coefficient star. In light of these advancements, the journey towards the Centaur's alpha coefficient Chiang Mai no longer seems like a distant dream.